We have clean, model-ready data, and we know the mistake we care about most, approving someone who then defaults. So which model should we actually use? We don't guess. We hold a bake-off, a fair head-to-head contest, and let the data crown the winner. 4 candidates step forward. Logistic regression, our simple linear model. K-nearest neighbors, which predicts by looking at similar past applicants. A decision tree, asking yes or no questions. And a random forest, a whole committee of trees voting together. We've already met each one earlier in the course. Now they compete on the very same problem. A contest is only fair if the rules are identical for everyone. So we fix them up front. Every model trains and is scored on the exact same 5 folds of the data. We pick one single metric before we start, so nobody gets to move the goalposts. And we set a baseline that every candidate has to beat, or it isn't worth using at all. Here's the tempting metric to reach for: accuracy. But on this data, it lies to us. Out of 500 applicants, 385 repaid and only 115 defaulted. So imagine the laziest possible model, one that just approves everyone. Watch its accuracy climb, 77%. And now watch its recall, the share of real defaulters it actually catches, 0. It flags nobody, yet it scores 77%. Accuracy alone would call this useless model a success. So we choose a smarter metric, the rock area under the curve, or AUC. It asks one honest question: can the model rank risk? Picture every applicant on a risk axis. A good model pushes the real defaulters, in red, to the right, and the people who repaid, in green, to the left. AUC measures exactly that. Pick a random defaulter and a random repayer. How often does the model score the defaulter higher? That fraction is the AUC. A half is a coin flip, 1 is perfect. And it never depends on where we draw the approve or decline line. To score a model without fooling ourselves, we use cross-validation. We split the training data into 5 folds. We hold one fold out, shown in yellow, train on the other 4, and predict the held-out fold. Then we rotate, so every fold gets its turn as the held-out set. We pool all of those out-of-fold predictions into one honest score. No applicant ever helps grade itself. Every model gets graded this identical way. Now we run it. Each bar grows to that model's real cross-validated AUC, not a number I typed in, but the true output of the algorithm on this data. K-nearest neighbors, first. The decision tree. The random forest. And finally logistic regression. Every bar clears the coin flip line, so all 4 learn something, but they are clearly not equal. And the winner is the simplest model of them all, logistic regression, at 0.768. That surprises a lot of beginners, who expect the fancy forest to win. But K-nearest neighbors actually comes last here, with many features on mixed scales. Its idea of nearby gets blurry, and the tree and forest never manage to beat the signal, because the pattern in this data is very nearly a straight line, which is exactly what logistic regression is built for. Now, a warning, because the metric you pick can flip the result. Here are the same 4 models scored with F1 at the default 0.5 threshold. Suddenly the decision tree looks best, and logistic regression drops behind. But this is an illusion. A tree's leaves output hard 0s and 1s, which easily cross the 0.5 line, while a well-calibrated model rarely predicts above 0.5 on a rare event. This score depends on a threshold we haven't even tuned yet. AUC doesn't depend on any threshold, so AUC is the honest ranking, and that's the one we trust. So we crown logistic regression, for 2 reasons. First, it ranks risk best. It earned the highest honest AUC. Second, it is transparent. We can read its coefficients and explain exactly why any applicant was declined. That second reason is not a nicety. Lending is regulated. A bank is legally required to tell you why it turned you down. A model whose reasoning you can read wins that argument outright, even against a slightly stronger black box. Let's lock in the workflow. Compare every model on the same split, the same folds, and the same metric. Choose that metric for the real goal. Here, AUC, never blind accuracy. Let the winner be derived, with bars growing to real scores, not asserted in a slide. And remember that the simplest, most interpretable model can absolutely win. Next, we take our winner and tune it, its settings, and the decision threshold that turns a risk score into an approve or decline call.